one of the other three. Okay? All right, chapter 2. Here we are. This is, now we're just learning the fundamental, basic way how these, once you have these constraints and you have the objective function, how you find the optimal solution for the variables. This is kind of a long way to do it. Before we do that, I want to refresh some math calculations. It's been a while for some of you, I'm sure. I'm going to put two equations up here. 18, and this one's going to be x1 plus x2 less than or equal to 8. Okay. We're going to pretend these two equations are two lines on a graph. And somewhere on that graph, these two lines cross each other. And you're about to see that we're going to graph all the constraints, and we're going to graph the objective function. And we'll see all these lines on a graph somewhere where the lines are crossing, and you're going to see that they're crossing maybe in 5 different areas, 6 different places. Somewhere where the lines are crossing is your optimal solution. Is exactly what you want to schedule production next year. It's where the lines are crossing. What you're learning today is to figure out which one of the areas where the lines are crossing is the optimal solution. How do you determine which one it is? By the way, a spot where two lines are crossing on the graph is called an extreme point. If it's touching the feasible region, it's called an extreme point. And one of the extreme points is your optimal solution. In the old days, we used to calculate every one of those extreme points. And then we would take the answer for every one of those extreme points, let's say there's 5 of them, plug them into the objective function and figure out which one of those makes that objective function either maximize or minimize, depending on what kind it is. Whichever one of those extreme points answers maximize or minimize the objective function, we just found our optimal solution.
So when the 2 points touch in what?
2 points touching each other on the graph.
There was another term you used.
Let's say there's 5 extreme points touching the feasible region.
Feasible region, that's it.
You're going to get that. I'm just throwing them out there to introduce you to them. The ones that are touching the feasible region, the extreme points, is where the optimal solution is at. And I'm going to teach you a shortcut to find which one of the extreme points it is, so you only have to do this once. You don't have to do it for every extreme point. Now, there's 3 different ways to take these equations and find where they cross, where they intersect. There's the substitution method, addition method, subtraction method. I'm going to go kind of fast. It is taping. You can review it on there. But you need to select which one you said, oh, I understand that. The one that jumps out and says, you understand it, write big notes, that's the one you want to use. Because you'll get the same right answer as someone else who's using either of the other 2. All 3 of these will get you to the right answer. It's just which one do you feel most comfortable using. All right, I'm going to start by using the substitution method right here. This one's the first one I'm giving. Right? There. You can take either one of these equations and you do algebra to it to get one of the variables all by itself on one side. Now, you don't have to do this, but I like to take these and turn them into equal signs just so I'm looking at equations. The less than equal comes into play later where you then shade a direction or another to represent all of the less than or greater than. Right now, I just want the line, so I'm making them equals. I'm going to take this one because it looks easier, the bottom one, and I'm going to give one of these variables all by itself on one side. So for me to get, let's say I want to make x1 all by itself, I obviously, to get rid of this one, I must have subtracted x2. Whatever you do to one side, you've got to do to the other. So if I subtract x2 here, I have to subtract x2 here. What do I have on the right side? 8 minus x2, the variable x number 2. Now I just got a variable by itself. Here's where the substitution method comes in. You substitute what that variable represents for the other equation you didn't use for that variable. And you're eliminating then the variable itself. So I'm now going to substitute this in for x1 in this equation I didn't use. So instead of 2 times x1, since x1 equals that, 2 times 8 minus x2, then I put the rest of the equation there, plus 3x2 equals 19. Now that I substituted that equation in for x1, x1's gone. And I can solve this for x2. And once you know what x2 is, You go back to either one of these equations, plug in that answer for x2, and you can now solve for x1. That's called substitution. Here we go. 2 times 8 is 16. 2 times negative x2 is negative 2x2 plus 3x2 equals 19. I'm going to combine like terms. I have a negative 2x2 and a positive 3x2. All I have left is 1 positive x2. I'm going to subtract 16 from both sides because it's a number, and so it can go to the other side. I got to do it to this side, and what do I have left? x2 equals 3. I just found where those two lines are crossing on one of the axes. If this were a graph, well, this is going to be off camera. Darn it. That's all right. Here we go. I'm going to make this one x1, this one x2. I just found x2 equals 3. 1, 2, 3. Somewhere along this horizontal line is where these two lines are crossing. Somewhere there, in that spot. Now I've got to find the vertical, which is x1, and I'll know exactly where these two lines cross. I'm going to plug 3 in for x2, either equation, and it'll be the same answer. It'll be easier to do this equation here, but I could have done it at either one of them. So now I have x1 plus 3 equals 8. Subtract 3 on both sides. x1 equals 5. I go over here. Got to make sure these are evenly spaced. 1, 2, 3, 4, 5. I go up, go here. Now, if I were to graph these two lines, they would be crossing at that spot right there. And if these two lines, which represent constraints, happen to be the two that are the most important constraints, and sometimes you got 50, and they're called the, I can't think of the name right now, but those two constraints, if we drew them up there, they would be intersecting right there at 5, 3. And this point, you write it like this. x1's first because it's the horizontal axis. x2 is second because it's the vertical axis. At that point, we're scheduling 5 doors and 3 windows for production. This is what we were solving. Get it? That's how this works. And this is very minor. I mean, this is very micro. You're going to see a problem where you can find this 5, 3 on your own. You can probably visually figure it out. But you got to remember, in the real world, this is huge. You need to know how this is coming about, how this works. All right. Oh, that was substitution method. I'm erasing this because we got to do 2 more methods real quick. Anybody need anything else to take a picture? We good? We good? All right. Here we go. Now we're going to use the next method, which is the addition method. The addition method says, take these 2 equations, change one of them so that when you add them, it eliminates one of the variables. So think about it. If I add 2x1 plus another x1, that's 3x1. I still have x1 involved. If I add 3x2 plus 1x2, that's 4x2. I still got x2 involved. I want to be able to do that same thing I just did, but one of the variables disappeared. In order to do that, I got to change. I'm going to change. You can change either one, but I'm going to change the second equation. And if I multiply any part of this equation by something to change it, the whole equation has to be multiplied by the exact same number to change it. You can't just change part of it, the whole thing. So I'm purposely going to multiply this equation by -2, because I know this x1 then would be -2x1, and when I add it, x1 will disappear, and then, but I got to multiply everything by -2. If I multiply any part of it by -2, I'm going to multiply the whole thing by -2, just to get to that point to where I can add and get rid of a variable. So now this becomes -2 times x1 is -2x1. -2 times x2, so this ends up being -2x2 instead of plus, right? -2 times 8, this equals -16. So this equation right here is now gone, and now I have these 2 equations. And now when I add these equations, add, x1 will disappear. Because 2x1s plus a -2x1 leaves 0x1s, which means it's gone. 3x2s plus -2x2s leaves 1 positive x2. 19 plus -16 equals 3. There I am, x2 equals 3 again. I plug in 3 into either equation for x2, x1 will come out at 5, just like before. Everybody see it? The hardest one about this one is realizing what you got to do to change one of the equations so that when you add them, one of the variables disappears. They turn into 0. That's the key to that. And the one we're about to do, subtraction, same thing. The concept's the same. You're going to change one of the equations if you have to, so that when you subtract them, one of the variables disappears. Same concept. There we go. Right here, right here. And then you still see the equation. Now I want to be able to subtract them so that one of the variables disappear. 2 minus 1 still leaves 1x1. 3 minus 1 still leaves 2x2. It doesn't eliminate a variable. So I'm going to multiply this whole equation, the bottom one, by 2. Because I know that 2 minus 2 would give me 0 and eliminate one of the variables. And then the rest of it will fall wherever it falls. Well, again, instead of negative 2 like before, I'm using positive 2 because the concept's the same. I'm trying to get rid of a variable. This ends up becoming 2x1 plus 2x2 equals 16. So now this is gone, and now I'm subtracting. 2x1 minus 2x1 is 0x1, and x1's gone. 3x2 minus 2x2 leaves 1x2. 19 minus 16 equals 3. Same exact answer. We plug in 3 for x2 in either equation, you would get x1 equals 5 again. No matter which one of these 3 you just thought, well, that you thought was the easiest, is the one you want. Really good notes on it. Remind yourself when you're solving, when you figure out the binding constraints, there's the word I couldn't think of. The binding constraints. The binding constraints are the constraints that are forming the optimal solution. You have constraints crossing over here, you got constraints crossing over here, you got constraints crossing over here. Whichever 2 constraints are crossing, forming that optimal solution, those are the binding constraints. They're the most important constraints because they're forming the optimal solution. We all got this substitution, addition, subtraction method, and we know it's the videotape can be reviewed, right? So we can make sure and pick one of these that you have in your future where you're going to have a question that says, hey, we discovered that these 2 equations are our binding constraints. Well, what would be the optimal solution where these 2 constraints cross? And you just got to apply one of these methods to it and figure out what the 2 variables equal. Okay? And you can check it if you want using Excel or using the software, but I need to see some work that shows me you can get to that optimal solution. Really, the work is also, I need to see that you can identify which constraints are binding. That's going to be a big deal with Chapter 2. If you're identifying, this is where we're heading right now, is identifying which of the constraints are the binding constraints. Next, I want to review how to graph an equation. I'm just going to pick an equation at random. I'm picking that top one, right? How do I graph it? I know some of you, it's been a long time, and some of you are going, oh, I can't do what we're doing. It's too easy. It's all right. Some people are going to appreciate it, so don't give them a hard time. You ready? The easiest way to graph an equation is you set up 2 points. And here's x1, here's x2, right? You make x1 0 and plug it into the equation, solve for the other one. You make x2 0 then, and plug it in for x2 and solve for x1. And you found 2 points that are crossing the axis. You connect those 2 points and you just graph the equation. That's how you do it. You ready? I'm going to start by putting a 0 in for x1. 2 times 0, if I put a 0 right there, is 0. Eliminated. All I have left is 3x2 equals 19. Divide both sides by 3. x2 equals 7.5. No, that's not it. Help me out. Is that it? No. No. What is that? 6.67 maybe. Help me out. 3. Thank you. Is that it? All right. So right here, 0, 6.333. When x1 is 0, x2 is 6.333. So x1 is 0, 1, 2, 3, 4, 5, 6.333. There's that point right there. Now I got to do the other variable. So I'm plugging a 0 now. Get this out of here. I'm plugging a 0 in for x2, solving for x1. 0 times 3 is 0. All that's left is 2x1 equals 19. So I divide both sides by 2. x1 equals 9.5. Thank you. 9.5. So when x2 is 0, x1 becomes 9.5. x1 is right here. 1, 2, 3, 4, 5, 6, 7, 8, 9.5. All right? I should leave that point right there because this is where these two lines are going to cross. So I actually got a little help right there. I need to go through that spot when I connect these, which looks impossible right now at first glance. Let's take a look. This graph is so bad, it's not even going to make it through that point. Damn it, that's bad. Why am I doing two lines? I don't know. I got to do this in one stroke. Hang on. Notice I'm going beyond the points, as each of you should. These lines continue on; they don't stop. Right here. All right, that's close. All right. So there's that one. Now I got to do the other one. Here we go. x1, x2. There we go. 0, comma, 0, comma. I just put a 0 in for each variable, so I'm looking at finding these 2 points. So I can find the 2 spots. I'm doing this one now. x1 plus x2 equals 8. Put a 0 in for x1. All I have left is x2 equals 8. That was too easy. Now I'm going to put a 0 in for x2. All I have left is x1 equals 8. Boy, that was too easy. So 8, 0, and 0, 8. Here we go. 1, 2, 3, 4, 5, 6, 7, 8. There's our 8, 0. 1, 2, 3, 4, 5, 6, 7, 8. There's our 0, 8. Now this also has to go through that point, because that's the point where they cross. Jeez. Well, that's not on the camera. I've never getting any good scores from my artwork, that's for sure. Unless it's abstract. All right. And there's where the 2 points cross, and where they cross, let's say this was a big problem, and this is just 2 of the constraints, and we somehow identified that these are our binding constraints, and we want to check where they're crossing. Happens to be one of the extreme points, which I'll show you in a minute what that means. And we go, okay, there's our optimal solution. Let's figure out what that point is. And you're looking at the graph, you go, oh, it's 3, 5. What is it, 3, 5? Or, no, I already forgot. 5, 3. It's 5, 3. It's obvious. Never rely on your visual of that graph. You must show me that you can calculate what that point is by doing either the addition method, subtraction method, or substitution method. Because it's very easily that could be 5.25 and 3.67, something like that. Even though it looks like it's right there, 3.5. All right, here we go. Blah, blah, blah. This is all the stuff you're reading at home before you got me. Blah, 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 blah. Here's an objective function, and this particular problem has 3 constraints. What a coincidence that 2 of the constraints happen to be the equations that we were using. Purely coincidence. We're going to start with the first one, x1 less than or equal to 6. Boy, I want you to see this, because a lot of people are going, where's the other variable's not there? How do you graph this? How do you graph this? When you only have one variable, and it says x1 less than or equal to 6, forget the less than. x1 equal to 6. I'm just going to find points where x1 equals 6. Because x2 is not in there. x2 can be anything. Whatever x2 is, as long as x1 is equal to 6. So that's right. So you'd have 6, I always just throw in numbers. 6, 4, 6, 2, 6, 1. I always throw in 0, 2. But. So then you would just go, okay, 1, 2, 3, 4, 5, 6. There's 6, 0. There's 6, 1. There's 6, 2. There's 6, 3. And it ends up being a straight line up and down, because it only had one variable involved. It's either going to be, when there's only one variable, it's either a straight line is horizontal or a straight line is vertical. but you just gotta analyze it, and it's saying that x1 has to be less than or equal to 6, make it equal, and x2 can be anything. So that's how that is graphed. The shading, you go back to the original equation, and you say, okay, is it less than equal or greater than equal? And this one happens to be less than equal. Then, once you have your line, you pick a point on either side of that line. Over here or over here. I'm purposely picking a point over here. Get it? Any point. Is this point right here, is it on the right side of that line? Right? Everybody see it? And what is this point right here? It's 1, 2, 3, 4, 5, 6, 7. 1, 2, let's make it 7, 3. That point right there is 7, 3. Plug that point into the original equation for the variables. Well, there's no variable to plug in for the x2, which is the 3. But x1 we can plug in as 7. Now ask yourself, is this true? Is the 7 less than or equal than 6? Yes or no? No. Then that is not the direction you would shade. And you don't need to even test the other side, because if you find out one side of the line is not true, then you know to shade the other direction. And had I picked a point over here, the x1 would have been 6 or less, and you would have said, oh yes, it is true, and that's the direction you're shading. You don't even need to test the other direction. So that's why the shading goes this way to represent the less than. The line is the equal. Okay. Next equation. We did this one. Which one did we just do? Was it that one? Did we just do this one? We did. What did we get? We got
3, 5.
Was it this one right here, which was 6.33 or where's this go? No, it was this one then. What is it? 9.5 or 9.5? 9.5? That was the simple one, isn't it? No, I guess the other one was 8.8, wasn't it? So it is. Okay. As you can see here, 9.50, like you just said. And then we got 0, 6.333. Remember those were the 2 points we had? But which way do you shade? The original equation was less than or equal to 19. To make this easy, I jumped down to right here. This is my favorite point to use, because ones are so easy to throw in there real quick and see if it's true or false. I throw in 1. 1 times 2 is 2. 1 times 3 is 3. 3 plus 2 is 5. Is 5 less than or equal to 19? It's true. We know to shade this way. We don't even need to test the other side. Had we picked a point here, 10, 1, and plugged it in, it would not have been less than or equal to 19, and we would have known to shade the other way. Show me a little work that you test a point if it's not so obvious. You know, that you tested a point, so you knew which way to shade. You have this in the future. Now the last one, we got 8.0 and 0.8. There are the 2 points. We had to figure out which way to shade. I'm purposely picking a point out here, 9.1. I'm throwing in a 9 for x1 and a 1 for x2. I add them together. 9 plus 1 is 10. 10 is not less than or equal to 8. So this ends up, right here ends up not being true. So that's not the direction we would shade. It's got to be the opposite direction. So we just graphed 3 constraints. We picked a point on one side or the other to figure out which way to shade. Now, this is where getting experience with these will help you, because when you're shading, you're saying, don't shade too dark, because you're actually shading in areas that are not part of the feasible region and areas that are. The feasible regions determine when every constraint's been graphed, and the shading for every constraint overlap. That's the feasible region. Let me say that again, because there's places where 2 constraints will overlap and there's shading overlapping, but it's only where every constraint's shading overlaps. Everybody hear that? So if I have 6 constraints, there's going to be 6 shadings going on. That's why you want to do it lightly, because you're trying to find which area all 6 shades overlap, all of them. And only the feasible answer is somewhere in that area. It's called the feasible region. So again, here's this one off to the left. There's that one. Now remember, we shaded this whole area up here. We can already tell that this is not going to be part of the feasible region because it's not. The shades aren't going to be overlapping. And the third one, we already took out some more And when they all overlap, is only in this area. So all of this now no longer needs to be, and for you, I don't want you to have to start erasing things, especially if you're using pen. I want you to outline your feasible region by making the edges of the feasible region dark, so it's obvious. And a lot of people will put FR and put an arrow into that dark, inside that dark frame to showing that's the feasible region. There's going to be a question in your future where it says identify the feasible region. And that's where I want you to put those dark lines. Look at what happens here. Had you gone too high and over, you would have been showing a part of a feasible region that's not, because only 2 of them are overlapping right there in that little triangle, not all 3. It's got to be where all 3 overlap, because there's 3 constraints. I want to make sure everybody gets this. If there were 6 constraints, 7 constraints, 10 constraints, the feasible region's only where all of them overlap. All of them. Every single shade are touching each other. And that's where the optimal solution is. It's in there. Someplace. And now to make this easier, the optimal solution is actually any place where 2 lines are crossing, touching the feasible region. So now the optimal solution is either here, 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 or here. We just broke down this whole feasible region to 5 points. That's our optimal solution. One of those 5 points. And in the old days, we'd start figured out each one of those 5 points. We know this one's 0, 0. That's easy. And we plug in, where's our objective function? When we go back to our objective function, we plug in 0, 0. And what you're going to see is if it's a min, that may be our optimal solution. But if it's a max, there's no way that's it. So now we got it down to 4. 1, 2, 3, 4. And we know that this is 6.330, I think, right? Because we put that dot there. And we know that this is 60. That's 0, 0, 6333. This is 60. But we don't know this. We don't know this. We can plug in a 6 for x1 and a 0 and get our objective function value. We can plug in 0 and 6.33, get our objective function value. What is our objective function? Max or min? It's a max. This is probably profit or revenue or something. We would plug in whatever x1 is here, multiply times 5. Whatever x2 times 7. The number we just calculated is called the objective function value. Meaning this is what the objective function would turn out to be if that were the point in which you're selecting as the best solution. So we plugged in 0, 0. We know that's not it. We plugged in this x1 was 0 and x2 was 6.33. We multiplied times 7. We figured out what that is. We plug in 6 for x1, 0 for x2. Do the math on that. And now we got those 2 other points. And we have to figure, those are the ones where we got to figure out what that point is, even though you can look at it and kind of guess it, but never rely on that, and what that point is. You say to yourself, what 2 constraints are forming that point? Okay, it's that one, x plus x1 plus x2 equals 8, and that one, the 2x1 plus 3x2 equals 19. Well, let's take those 2 and do the substitution method, addition method, or subtraction method, figure out what that point is where they cross, and we figured it out, and what did we get here? Was it 5, 3? Was it? 5, 3. But what about this point? Well, we know it's 6 something. So we're going to take the equation x1 equals 6, and then that equation is this one, and either use, it's very easy to use the substitution method, x1 equals 6, just plug a 6 in there, figure out what x2 is, and you know that point. Then I could plug in that point and that point into my objective function and figure out which one gives me the bigger objective function value. You then found the optimal solution. You're saying to yourself, boy, that's going to take some time. So here's a shortcut. You ready for this? You don't have to do the math on every extreme point. Instead, you take the objective function and you set it to any arbitrary number so that the line, you can just see the angle of the line. This is all about the slope of the line. Because no matter what you make the objective function equal to, this line will be parallel to itself. If you make it equal to 35, there it is. If I made it equal to 40, it'd be right above it, but parallel. If I made it equal to 20, it'd be right below it, but parallel. No matter what you make the objective function equal to, and this is where everybody falls apart. You make the objective function equal to whatever you want to, and every one of you can make it equal to a different number. It's arbitrary. It's arbitrary. It's just so you can find the slope of the line. It's just so you can see which angle is going to land on your graph. Then once you have that slope, you go, okay, is this a max problem or a minimized problem? Well, let's see, on this side of this objective function line is this extreme point and that extreme point. And this one is making our objective function smaller. But this is a max problem, so our optimal solution is probably on this side of the objective function, which leaves me with there, or there. So our optimal solution is probably one of these three, since these three make the objective function larger, and it's a max. Now, this is so big, I don't have a big enough straight edge. But you take a straight edge, if you're working on paper, and you start moving this line outward, or if you want to do it the long way, start making this equal to bigger numbers, and drawing lines here parallel, until you get this line to completely leave the feasible region, except for that last little second that it's still touching the feasible region. It will be right there at one of those three extreme points. It will be outside the feasible region except for just touching it. The very last one of these 3 points will be the last spot that line touches as it's leaving. There's your optimal solution. Looks like this. Here it is, getting closer and closer. You can almost tell now. You can tell that that can't be our optimal solution, can it? It's one of these two now, and they're so close to each other, they're almost parallel, so this makes this really hard. But if you keep going, the very last one it would touch as it's leaving is that point right there. That is your optimal solution out of the 5 extreme points. And this is the one you got to say, okay, which equations are forming that point? I don't need to calculate what that point is. I don't need to calculate that one. I don't need that one or that one. All I need is that one. Which two constraints form that? Either use the addition method, subtraction method, or substitution method and find that point. And now you have the optimal solution. You're not done though. You then say, okay, the optimal solution is 5 and 3. We calculated that point already because those two happen to be the binding constraint. And so we identified, oh, it's these two constraints, right? We went right here and we said, oh, it's these two constraints right here. This one and that one. We have to take those two equations and we got to use the addition method, substitution or subtraction. Let's do it. 3, 5, or is it 5, 3 or 3, 5? 5, 3. And now we got to go back and plug in 5, 3, 5 for x1, 3 for x2 in the objective function and get that objective function value. Let's go to the objective function. Plug in 5. 5 times 5 is 25. Show me you're doing this, that you realize it. Plug in 3. 3 times 7 is 21. 25 plus 21, 46. The maximum profit, or whatever this represents, revenue profit, the maximum we can get with these limitations is we got to make sure and have 5 x1s and 3 x2s. And there may be another combination of x1s and x2 that could be an alternative optimal solution, but it will not get us a better objective function value. It may tie. So we have the very best this objective function value can max out to with 5 and 3 as our optimal solution. And that's what this is all about, is finding that optimal solution. We're going with 5 and 3. There's our decision. Going here, shading, where they overlap, feasible region, extreme points. We got to figure out which extreme points are optimal solution. We graph that objective function value. I want to give you a hint. 5x1 plus 7x2. An objective function is not equal to anything, so now you're going to make it equal to some arbitrary number. My hint is, I always look at these numbers and say, what did they both go into evenly? Oh, 5 times 7 is 35. And it just makes it a lot easier to make it easier to a number. You know they both go in evenly. It just makes it faster. Or I may say, what else would they both go into? 7 times 5, how about 70? They both go into 70, right? But then my line is out here. It's parallel with this line, but it's not in the feasible region. And then you have to realize, oh, my optimal solution is out here because it's a max problem. You're bringing your line down. It's going to be the very first spot it touches the feasible region, which is still going to be right there. as you bring it down. I always like to put my objective function in the feasible region, then determine which way I'm going based on whether it's a minimize or a maximize. That's how. So I try to pick a number that I say to myself, what will put, where will it land here? Will this line will cross here, so I know then which way to go. And sometimes I end up out here and I just know I gotta get a straight edge and go backwards is all. So 35, okay, let's make it 35. All right, we got a 5, let's see, we got a 0 here and a 0 there, just like we did with any of the other ones. Put a 0 in for x1, that's gone. Divide 35 by 7, we get a 5. Now put a 0 in for x2, that's gone. Put a 35 divided by 5, that's a 7. 0, 5, 7, 0. Here's 7, 0. Here's 0, 5. Draw your line. You go, okay, which way? It's a max problem. This always makes the objective function bigger compared to this. So I'm going this way. Grab a straight edge. Okay, I'm past that, I'm past that. Just past that one. It's between these two. Get a little closer. Look at it, I'm passing that one. I know it's either that one or that one. And as we're moving out with our straight edge, and there it is, there's the very last spot we're touching. If it's so close, let me go back one. If it's so close, I'm not sure if it's this or this, just find what that point is, find what that point is, which is an easy one. Plug it into the objective function, whichever one gives you, because this is a max problem, whichever one gives you a bigger objective function, that's your optimal solution. If you're saying my drawing's not good enough, I can't tell between these 2 points, plug them both in. Figure out what those 2 points are, put them both in. If it's a max, it's the biggest one. If it's a min, whichever one gives you the least, is your optimal solution. So, there it is. Blah, 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 blah. Okay. When we graphed it, this is the same one. We graphed it, it's just not showing all the lines. There's the same feasible region you've been seeing. It's just pointing out that there are 5 extreme points that we're touching, where 2 lines were crossing and touching the feasible region. This part of the PowerPoint is just showing you there were 5 possible optimal solutions. And if you were able to find all 5 points, you don't have to do that objective function and move it out. You can plug in 5, 3, 6, 2, 6, 0, 0, 0, and 0, 6 and a third in the objective function 5 times and figure out which one gives you the best solution. Since it's a max problem, whichever combination of numbers will give you the biggest amount of the objective function. Am I losing anyone? When you walk out of here, do you remember this? Where are we at? I gotta keep going here. Let's see. We want to do this. Let me look at my notes. I don't want to go too far. How are we doing on time? We got time. Was there an in-class pay?
No.
You sure?
I think so.
Did anybody look up Blackboard?
I think it's on Thursday.
Okay, just check. Okay, here we go. Well, let's just look at this one. Let's go for it here. Do it again. You ready? Let's start with, where's the I want to graph, let's start with, is this the same equation? No, that's different. 2x1, let's go 2x1 plus 5x2 greater than or equal to 10. Is that what that says? Now, I like to make it equal to 10 when I'm trying to figure out to graph the line, so I'll just pretend that's an equal. I'm going to put a 0 in for x1, figure out what x2 is, and then I'm going to put a 0 in for x2. This is x1, that's x2. Then I'm going to figure out the 2 points, and then I would connect them. So x1 is 0, that makes this disappear. I divide 10 by 5, x2 is 2. If I plug a 0 in for x2, that's gone. It says 2x1 equals 10. I divide both sides by 2. This is a 5. So that first one graphs at 0, 2, 5, 0. 0, I already forgot. 0, 2. So that's right here. And then 5, 0. 1, 2, 3, 4, 5. Connect my line. Ah. Which way should I shape? Pick a point on either side of this line. I love 1, 1. Plug it in and determine if that's the direction to shade or not. 1 times 2 is 2. 1 times 5 is 5. 5 plus 2 is 7. Is 7 greater than or equal to 10? Yes or no?
No.
So that's not the direction to shade. The direction of shade is upward. Next one. Now we're getting into negatives. This will be your first time seeing negatives. We'll see what happens here. 4x1 minus 1x2 greater than or equal to 12. I just look at it as an equal. Again, I'm plugging a 0 in for each variable. 0 in for x1 leaves just negative 1 equals 12. Divide both sides by negative 1. x2 equals negative 12. Is that right? Don't worry, we're going out of this quadrant. Your optimal solution's in this quadrant, but sometimes your points are down here. You just extend the line into this quadrant, the positive quadrant. I'll show you in a minute. We're putting in a 0 now for x2, which eliminates minus x2, leaving just 4x1 equals 12. Divide both sides by 4, we get a 3. 0, negative 12, 3, 0. The 3, 0 is easy. 1, 2, 3. Now, what is it? 0 and negative 12? This is going to be tough. Down here, this is 1, 2, 3, 4. They got to be the same space as these, even though it's 5, 6, 7, 8, 9, 10, 11, 12. It's way down here. I put my dot. Now, I'm going to connect these dots and extend my lines. The key is I have to extend that line up into this region. Here we go. There. Even though the negative's way down here, it's just giving me the angle, the slope of that line, so I can get it into that region. And then we would do the third one, 0, 4, 4, 0. And it would look like this. Here's our 5, 2, just like ours, right there. And we said the shading goes upward. Here is the negative 12, 3. And had we evaluated which way to shade there, it would have went this way. And then the 4, is it 4, 4? Yeah, 0, 4, and 4, 0, there it is. And had we evaluated that one, the shade would have gone that way. All the 3 constraint shadings overlap here. Here's your feasible region. You've got to identify it. Dark lines. Look at that little triangle. I want to make sure you guys see this. I'm looking at everybody here. You guys are on. Right. You have a little triangle right there? That's outside the feasible region. There's 2 constraint shades overlapping there, but not a third. And you can, so when there's 2 different points, extreme points right there. You see it? I don't know if you guys can see that. Here's an extreme point. There's those 2 little ones, and that's it. I don't see any other extreme points. Our optimal solution is either here, here, or here. One of those 3. This one's easy. This is 5, 0. I can plug in a 5 for x1 and a 0 for x2 in the objective function, see what it equals. This is a minimize, right? So whichever one of these 3 points gives us the smallest objective function value is our optimal solution. Or we can take the objective function, graph the slope, a line, and work it. This, we'll see that we need to go that way because it's a minimization problem. The more we go this way, the more the objective function is going down. And we would find that one of these 2 little points right there is our optimal solution. And which one is it? Again, whoops. Let's grab, there's our objective function. We made it equal to some arbitrary number. We see that it should be at 4.50 and some number way up there. We connected the dots, we got our angle. It's a minimization problem, so we know we got to go this way. We're already past this extreme point, so our optimal solution is not there. We got it down to these 2 little ones right here. We keep going. If we have a straight edge, here we go. I'm trying to keep exactly the same angle. The whole thing's moving. And I get that top little one being the very last one we would touch if we were leaving. I think. I don't know if that's true. Sure enough, it is. If we had a line that, as it's leaving, the very last spot it would touch is that top one out of those 2. We figure out what 2 constraints formed that point. We apply either the substitution method, addition method, subtraction method, and we found the optimal solution for that one. How do we feel? Can we solve these? Some of you are looking at me like I'm making it too easy. Some of you are looking at me like, I can't believe we got winners. This is crazy. Don't worry. Just 1 week of it. All right? So where are we at here? Let me look here. We only got a few minutes left, so use Excel, check your answer. Make sure you got the right optimal solution. The top part of this Excel spreadsheet I posted is where you enter the data. There's 3 constraints and an objective function. There's 2 variables involved. This is set up in case you have 5 variables. But just leave these blank if there's only 2 variables, x1 and x2. You can even change this to x and y or whatever the variables are in the problem. Constraint 1 had a 1 and a 0. Now, I want to make sure you know what I'm doing here. I'm going back to this original one we talked about here. Look at constraint 1. Constraint 1 has what number with x1? A 1. There's only one of them. And there's no x2, 0. So on Excel, you form that by putting a 1 and a 0. And that is less than equal to what? 6. You're entering this data at the top. The second constraint had a 2 with x1, a 3 with x2, and it said less than equal to 19. You've entered that data. The other one had just x1 plus x2 is less than equal to 8. So you put a 1, 1, and 8. The objective function had a 5 with the x1 and a 7 with the x2. I just want to make sure you see where I'm getting these from. There's a 5 and a 7. Got that all on there, right? And this works, by the way, if you have additional constraints, you just go insert column right here and put another row of data here. You can widen it up. This line, leave it the way it is with zeros. Your optimal solution will be here. If there's only 2 variables involved, these will turn into numbers, these will stay as zeros. If you got 3 involved, these will turn into numbers also. You could have an optimal solution for multiple variables. Now this one is where all the work's put in. It's the calculation for the objective function. It says you take E10, the objective function value 5, times the optimal solution for x1. Then you add to it the objective function value for x2, which is F10. And you multiply it times the optimal solution. And you add those together, and there's your objective function value. When you have Excel do this, it's plugging in every possible number in the feasible region for these 2 and calculating this in seconds. And whichever one gets this the largest, it will stop, and it will give you your optimal solution. It's also looking down here. These formulas down here are just like calculating constraint. It's plugging in the optimal solution for the variable, multiplying by its corresponding number. So you should see cell, it should be cell, what is this? E14 times E7. E7 times E14 plus F7 times F14 added together. And this is saying, and this is here just to remind you it's a less than equal. And here, this cell is looking up here to see what the right-hand side is. So here, this says equals J7. This one will say equals J8. This one says equals J9. Over here, constraint 3. This 1 times the optimal solution plus this 1 times the optimal solution added together, and it should be less than 8. It's all set up. These formulas are in there. If there's another constraint, just follow the logic here and write the formula, add a constraint right here. Follow the logic. It would be whatever those constraints numbers are times the optimal solution down here. Either add or subtract it depending on how the constraints are. And then you hit solve. To solve it, you follow the steps on page 89. I can't remember what they are. Let's see, data. I'm going to go by memory. It's been a long time here. Let's see. When was this? We did this in February last time. No, January. This has been since January. Anybody on page 89? Is it solver or data analysis? It's got to be data analysis. Okay, it's, no, that's not this one. Boy, it's not this one. Come on, someone help me. Which one is it? Solver. That's it. Here we go. Let me get these out of here. Let's start from scratch. Then you can't see these. Okay. You ready? Set objective. This is asking you what cell location has the objective function value calculation, which happens to be right there. What is that? E16? And it types in $E, $16. Next, is this a max or a min? This one's a max, right? Next, changing variable cells. Where do you want the optimal solution? Now, I want to tell you, I see no one taking notes. If you could easily have an Excel spreadsheet with this open, and it may ask you, what is it you type here? And you should be giving me the cell locations where the optimal solution is. So, where it says, by changing variable cells, it's changing these cells. Right there. E14 through I14. Now, constraints. Get over here. The first constraint, we're going to add a constraint. Right here. Cell reference. Where's the formula where that constraint's running? Right there. The first constraint's at, what is that? E20. Is it a less than equal, greater than equal? We're using these top three. Less than equal, equal, or greater than equal? It's a less than equal. And then it's less than equal, where's the right-hand side? Right here at, what is that? J20. We hit OK. There's that constraint. E20 less than equal J20. We got two more constraints. Add another. Cell reference. E21 less than equal. Let me get over here. This would be J21. Okay. We got to add a third one. This is going to be 22 less than equal J22. Okay. We have all three of them. There's no more. We have where the optimal solution is. We have where the objective function is. We told it that it's a max. You must make sure this box is checked saying make unconstrained variables non-negative. Our solutions for this class will always be non-negative. We're not going to have, hey, make -5 bicycles this week. Every one of our constraints will be 0 or above for this whole semester. Our variables will always be 0 or higher, positive. So we always have this box checked. Make unconstrained variables non-negative, meaning we're nothing below 0. We also got to open this up. Sometimes it says GRG, switch it to simplex LP, linear programming, which is what we're doing. Now when I click OK, you're going to see these numbers changing really fast, and then it comes up the screen saying, is it okay? You ready? It's going to go fast. That was way too fast. Click OK. Our optimal solution is x1 is 5. If you recall, that's what we got. x2 is 3. And if we plug 5 and 3 into the optimal solution, 5 times 5, 3 times 21, add them together, our objective function value is 6. And it's now solved.
Use this for an example?
You can, but this is not your work. You got it for that quiz. For the final, this is fine. For this quiz, I need to see that you are getting you're able to absorb how this is done the long way. I need to see that you understand how this is all coming about instead of just coming up with 46 like this. I need to see that you understand how this 5 and 3 and 46 actually came about. And it all really, through time, has come about from graph. We're done, huh? We're past time. I owe you a minute. I'm taking that minute that you will be back. See you guys.